Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Webb Space Telescope, the First Year of Science by Macarena Garcia Marin from the Space Telescope Science Institute and the European Space Agency. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I want to thank the wonderful tech team that brings you these webcasts, Thomas Marufu and Grant Justice. I also note that the Space Telescope Public Lecture Series will continue to be online only throughout the year 2023. Our upcoming talks in September, we'll have a talk on the interstellar medium, the stuff in between the stars, by Alexandra Hamonowicz, and I got to get that name right by next month, of the Space Telescope Science Institute. Actually, I don't have to get that name right because I will be on vacation on September 5th. You will have a guest host, so they will have to deal with that name that obviously I can't handle. On October 3rd, Nimisha Kumari will be giving a talk on Webb science. She hasn't given me an exact topic yet, but she will soon. On November 7th, we have our infamous TBD for both topic and speaker, which means that I've got to do some work this month to arrange speakers. So I will have that speaker as I always do. To find out who that speaker will be, you can go to our website, www.stsci.edu/public-lectures. This is our public lecture series webpage. And on the left side down bottom, as you can see, there are our webcasts, both on our YouTube playlist and on our webcast archive at STSCI. Down in the lower right, you can see the way to sign up for the email. Just type your email address in, hit that subscribe button, and you will get our probably twice monthly emails about our lectures. Also on our website is the list of the upcoming lectures. And if you click on each individual lecture for the read more, you will find the description of the lecture, the webcast after it has been recorded, both the STSCI webcast and on YouTube. Oops, wrong button. Our email, as I said, it's easiest enough to just sign up at our website and get the email announcements. If you would like another way to do it, you can sign up and subscribe to our YouTube channel. We're at youtube.com/Hubble Space Telescope, all one word, Hubble Space Telescope. You will get new video notices and reminders of live events such as this one. Also, if you have comments or questions about the public lecture series, you can send it to our email, publiclecture@stsci.edu. I'm also going to tell you about our social media. Within the Office of Public Outreach, we handle social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. And you can see the handles listed here for Facebook, Twitter, YouTube, and Instagram. I myself do a tiny bit of stuff on Facebook and Twitter at Dr. Frank Summers. Now the news from the universe for August 2023. And I just have one story for you tonight, and it's about Hubble examines the aftermath of the DART impact. Now, many of you may remember a movie from long ago starring Bruce Willis called Armageddon. And the plot of this movie was that an asteroid was going to hit Earth and we had to stop it. So Bruce Willis and his team go up and they land on the asteroid and they insert an explosive device and they blow the asteroid up and they save Earth. Unfortunately, that's not the way to save Earth. Because if you take an asteroid and you blow it into a million bits, well, then instead of one impact, you get a million impact because you're not going to blow the asteroid so far away that it's not going to stay on that orbit. All those millions of bits are going to stay on that orbit and they're all going to hit Earth, and that's going to be an even worse problem than if you didn't blow it up to begin with. So what you really want to do if you want to avoid an asteroid impact is you want to go to that asteroid and you want to gently nudge it out of the way. You want to change the orbit. You don't want to break it into pieces. You want to actually change the orbit so that it misses Earth, okay? But there's a problem with that, and that's sort of illustrated by this picture of the asteroid Ryugu. You can see that it's a small asteroid, but you can see there are boulders and pockmarks on it. We're not sure if these asteroids are solid bodies or if they are what we call rubble piles, that there is a significant amount of debris on the surface, right? So that if you actually hit it to nudge it out of the way, what's going to happen? Are all these other things going to become a big, huge cloud that gives you the same problem? Okay? So, folks designed a mission called the DART, the Double Asteroid Redirection Test, okay? In order to study what happens if you try and nudge an asteroid out of its orbit. Now, they did this with a double asteroid, Didymos, with the smaller asteroid Dimorphos, and Dimorphos is in an orbit around Didymos, and if the idea was that you would hit Dimorphos, slow it down a little bit, and then it would move to a smaller orbit around Didymos. Okay, so it's going to, the DART is going to impact it, it's going to slow it down, and then it will move to a smaller orbit around Didymos because you've taken away some of the energy. Now, these aren't huge asteroids. These are not the huge giant ones that you would see in the movies. Dimorphos is only 163 meters, 1.5 football fields, and Didymos is 780 meters, less than a kilometer, maybe about half a mile across, okay? So these are small asteroids. They're good for this kind of test because, as you can see in this image, the DART mission itself is only 19 meters across, and most of that is the solar panels, all right? And so it's going to be a small little punch into it, just enough to change Dimorphos's orbit just a tiny bit, but a measurable amount. All right, so this actually happened last September 26th, and these are images from DART as it was approaching Dimorphos on the left and just before impact on the right. Okay, and you can see that there are this boulder field on the surface of Dimorphos, right? So that you've got all this loose stuff, and that's what they're going to be able to study. How much stuff spews away? Well, they watched it very, very carefully. Matter of fact, this is both Hubble and Webb were able to watch it, and you can see the debris splaying off from Dimorphos after it had been hit. And the mission was a success because they did find that there was a measurable change in the orbit of the moon. All right, so what's this got to do with today, since this was last September? Well, Hubble did a follow-up observation about 6 months after the impact and got this image of Dimorphos. And you say, well, what does it show me? It's just got this bright thing here. It doesn't look like much. As a matter of fact, it didn't look like much to me until you note that these little white dots there, those are scattered boulders, okay? Now, these are 37 boulders that they were able to measure from about 3 feet across to 22 feet across. And these are drifting away very slowly from Dimorphos at about 1 kilometer a second, or about half a mile per hour, okay? So they're just drifting away. So the question is, how did they get there? Were they part of the ejecta that happened in that impact? That doesn't sound terribly likely to me because I think they'd be at a higher velocity there. Or they were sort of shaken off by the impact creating a seismic wave and then being, scattered off of it. That's something that we don't actually know, but Hubble's observation is giving us the information to study. And the European spacecraft Hera will visit the system in 2026 to examine the results in detail. And these Hubble observations, Look, that's an incredible resolution. We're seeing boulders 3 feet across, right, across the solar system. This is amazing stuff. And that type of observation will help Hera plan for what their observations will be in 2026 and really get the full detailed results of the DART impact mission. All right. Our speaker tonight is Macarena Garcia Marin, and she comes to us as the project scientist for the Webb Space Telescope. Yeah, that's an important position, okay? So you're getting the first year of Webb from the horse's mouth here today, okay? She did her studies in Spain. She is of Spanish origin, and did her work, thesis work on merging galaxies, something that I've always enjoyed reading about and studying as well. She started work on the mid-infrared instrument for the James Webb Space Telescope during that time, and she did a postdoc in Germany and continued her work on the MIRI instrument, as well as continuing her research. And then in about 2015, if I remember correctly, she came over and got a position here at the Space Telescope Science Institute. She has worked on the MIRI instrument since then, even becoming the MIRI branch manager. And recently, she moved into the project office, where she has become the project scientist for Webb. Outside of her science, she takes care of her 2 kids, as well as enjoying hiking and biking and swimming and outdoors. Like a lot of astronomers, we're all very prominent as nature lovers. So, ladies and gentlemen, Dr. Macarena Garcia Marin.
Thank you so much, Frank, for the introduction and for having me here. By the way, can you hear me okay?
Yes, we can hear you.
Okay, perfect. Thank you. So, of course, thank you so much to everyone who is connected. I really appreciate your time, and I'm very, very happy to be here to talk about the first amazing year of Webb science with all of you. So the presentation, we're going to talk a little bit about the telescope itself, quite briefly, and well, many of you probably will know everything about it, but just as reminders and for people who may not be familiar with it, and then we'll go right into highlighting some of the great science discoveries and great data we are taking with Webb. So let's go for it. Okay, so all about Webb. In a nutshell, what is Webb? Which is just, quote unquote, a large infrared optimized space telescope. It's large, it's like it has a very large mirror, 20 feet across, composed by 18 segments coated in gold. And I have this picture here with the actual mirror with an engineer next to it, so you get a sense of how big. It's really an impressive size. And the reason why it is important is because the larger the mirror, the more detail you can see, and the farther away objects you can actually measure in the universe. So in this case, you have a comparison with the Spitzer, Hubble, and Webb is so far the largest thing we have sent to space, also the most sophisticated. So that is for the large part. The infrared part. So what is infrared? As you know, light is composed by many different types of emissions. So we have, for instance, X-ray is a type of light. We have the visible light, which is the one we can see. We have ultraviolet, which is the one that burns our skin. So there are many types of different lights. So light is composed by, let's say, many, many different colors. So this is an example of what we would see with visible light if you have like a firefighter surrounded by smoke, essentially. If you switch to an infrared view, this is what you would see. So here you can see perfectly well the firefighter. You can see a person lying on the floor. You can see all the room, and you don't see the dust, the smoke quite well. So this is because the infrared is an actual excellent way of measuring temperature. You can really see the emission of all the bodies you have around you. And the great thing about the infrared is that everything that has a temperature, everything above the absolute zero, emits in the infrared. So the colder, the weaker, but it is there, you can actually measure it. Another example that I really enjoy always is this gentleman with his arm covered with a plastic bag. So on the visible, this is what we see, it's just, you see the plastic bag. in the infrared, you see both. You see the bag that is colder, and inside the bag you see the hand and the arm, because they are emitting thermal. They have thermal emission. They are emitting temperature, and you can actually see them both. So this is very similar to the effect that happens on the sky and in the universe. You can actually pierce through certain things. And finally, why infrared light is so great? Well, it resists temperature. So we can peer through the dust and see the dust itself, but also it's great to measure the first stars and galaxies. And this is a concept that often it's a bit, out there, but it's really nature helping us. So when the first stars and galaxies were formed and created, they emit their light in the optical. And so that light started to travel towards us in this universe that is actually expanding. So light is a wave. And because light is a wave, on that expansion, imagine that you're moving through a universe that is expanding, and that wave actually stretches itself. So it moves from the visible light to the infrared light. The infrared light, you can think of it as much redder than red, and we cannot actually see it. So this illustration here, it really shows an example of what Hubble could see, because Hubble is mainly a visible telescope, so it can see only through, at the edge of what the visible can show us, and it's not really the first galaxies or stars because they didn't emit. We cannot measure them that way. With Webb, we're actually breaking that limit. It's like looking down the cliff of what we can measure before seeing the first galaxies and stars, and you're going to see beautiful examples of data we are already getting and showcasing. So temperature, great to see dust and to see through the dust, and also measuring the first stars and galaxies. And of course, everything else. So everything from Mars and beyond, we can actually see it, including our solar system. And we're going to talk about that a little bit later. Okay, so I wanted to dedicate a few minutes to, because we talk a lot about, the infrared and the light and all that. And really, what a telescope does is to measure light, depending on the range. So in case of Webb, it's infrared, and light is photons. So the light carries a message, and that message is the message of our universe around, and it's really bringing us all that information we can measure. And how do we actually do it? So in the visible, if you use a red filter, you will absorb all colors except red, and then you could measure only the red color in that filter. So you can think of a similar thing for the infrared colors. So Webb's instruments to do imaging, we do two things, imaging and spectroscopy. So for imaging, Webb's instruments, they select the lights using these infrared filters. And you can see a representation here. You can see the visible is mainly optimized for Hubble. The Webb has a very broad infrared range that we can measure. And then beyond that, the Spitzer Space Telescope, which I'm sure many of you remember, it was a great observatory. So it had some overlap with Webb, but also it went farther into the infrared. So we do select colors of light using filters. And of course, those filters let the light through, and then it's measured by a detector. So we have two main techniques of taking images with Webb. One is like a straight image, this beautiful Carina Nebula. I'm sure you're very familiar with it. This is a straight imaging. So it's like taking a picture and combining many filters and many mosaics of the picture. The other technique is what we call coronagraphy. And it's a really often challenging and sophisticated technique that consists of let's block the light of the star and see whatever is around that. And in this case, we can see planets around. So one of the pre-launch question is like, how good are we going to be able to do this technique? And actually, as you can see here, we can do it very well, and we can see planets. And this was the first demonstration we had and shared with the public for coronagraphy. So direct imaging of exoplanets and standard imaging. Exoplanets, or things like if you have a very bright galactic nuclei, you can also block it and see what's around that nucleus. I also wanted to talk a little bit about the spectra, which again are usually challenging. And this video is just going to show you how do we do this spectra. Spectra is essentially like a rainbow. A rainbow is a spectra of the sunlight filtered through droplets of water. So for Webb, and this is an animation of MIDI, the mid-infrared instrument, you're gonna see, I'm gonna skip it a little bit because the beginning is a bit slow. So that's the instrument. And now you're gonna see coming through the right of the screen, light coming from the mirror of the telescope reflected in there. So that light goes into the peak of mirror and then enters the instrument. And now you're gonna see a lot of bouncing around because that light has to reach to the spectrograph we want to use. And there it reaches there, and the first thing we do is splitting it into 4 different colors, essentially. And then they keep on bouncing around the instrument because it's very compact and it has to fit certain size. And finally, we disperse it and obtain all these rainbows of infrared that you're gonna see now. And at the end, it goes to the detector, and in the detector, we measure it. It's a very impressive animation, but this is really what the instrument does. And this is just an illustration of, the light path and how it bounces around, but also how you have to really adjust your instruments to the size you have assigned for your for within the observatory. That's why it bounces so much, because it has to be very compact. So anyway, that's just an example of how we do a spectra with Webb instruments. And this is an example of the science you get out of them. So this is one of the first spectra that were made public. It's a beautiful spectra of a 13.1 billion years galaxy. And you see here how you can measure all these individual lines, and each of them, it's an element. You have oxygen, hydrogen, neon. And the great thing about this is that it really helps you characterize the chemical composition. It allows you to estimate the age, because you know where you measure these lines in the lab, and then you know how to measure it on the sky, and then you can measure the difference, because remember, the universe expands, so the light moves as the universe expands, and the emission line as well. So I wanted to highlight this because Webb is an amazing... Oh my God. Okay. An amazing infrared telescope, but about 75% of the science we do is actually a spectroscopy. And spectroscopy is like our main workhorse, and this is where you can actually measure all the details, composition, and age of those astronomical objects. Okay, where is Webb? Well, really far away. This is not to scale, but it is about 1 million miles away from us, in a really stable orbit that is called L2, the Lagrange point 2. So it orbits around that point, and it moves with the sun and the earth. In 1 year, you can actually observe any point of the sky, any astronomical object. I wanted also to show here that, so you can see on the illustration that you have the telescope and the sun shield. It's looking at the sun. Why is that? Well, we need to protect the telescope, the instruments, from the really intense heat of the sun. And this is how, an illustration of how it looks like. This is the hot side, sun shield, and this is the cold side. This is where I'm so sorry. Okay. So in the hot side, you have electronics, you have the star trackers, you have the telecommunication antenna, of course, the solar panels. In the cold side, that you can see here, very dark, you have the mirrors and the instruments and all the components that really need to measure that very faint infrared emission from the universe. So it has to be kept cold. The warm side is about, close to boiling water temperature. The cold side is about 500 plus degrees Fahrenheit colder. So if you think that your home freezer is about at 0 Fahrenheit, this will be like a minus 300 plus 300, less than 350 Fahrenheit. So it's really incredibly cold. And we need that to actually be able to do the science we need to do with it. Okay. So Webb is out there being, cold and quiet and dark on the dark side and really taking science, how do we talk to Webb? So we talk to Webb from Baltimore. Actually, for those of you who are connected from Baltimore, Maryland, I feel this is something to be very proud of, that, the instrument is, the telescope is operated from here, and all the, scientific operations, data processing, science organization, it just happens from here. So it's really great. And the way we talked with it, so twice a day, we communicate with the telescope, and to do that, we use a network of antennas. There are 3 of them. This is a deep space network. We use an antenna in California that is illustrated here, another one in Australia, another one in Spain. And that's how twice a day, our flight operation team, they upload commands and then download, if necessary, and then download all the data that has been, obtained during the day. Webb is essentially, it's not 24/7 quite, because sometimes you have to do commanding and other things, but for the most part, it's taking data all the time, and we have to downlink it. Okay, so that was it for the telescope overview. If you have questions, please let us know later, because now we're going to move into science. And this is the first anniversary image. It's a beautiful star forming region. We're going to talk about it a bit later. And the way we are going to approach this sort of science conversation or discussion of the first year is we're going to go near to far. That means we're going to start with our solar system, and then we're going to move to, with the planets of our solar system. Then we're going to move to exoplanets, stars, galaxies, distant galaxies. And we're going to have like this sort of orderly, if you want, approach to how Webb looks at things. So I wanted to mention one of the things, when it comes to solar system, it is actually very close to us, the closest objects we can measure. And one of the things pre-launch that we were always wondering is like, are these objects going to be too bright? Are we going to be able to observe them properly? Are we going to be able to see the faint rings around the planets? And the answer is absolutely. It's there, and it's beautiful. And you can see here Uranus and Neptune as descriptions. So the Uranus rings, we knew they were there, but we did not see them since the Voyager mission in the 80s. And this is like what Webb can do in a very short time. You can see the atmosphere, you can see clouds, you can see the rings perfectly, and you can actually measure it. And there are follow-up observations for this. To the right, you have Neptune. Again, you see the rings, you see very clearly some of the satellites, and you also see all these clouds shining in the infrared. So the great thing about this is that solar system scientists, they are actually taking these measurements and this data and all the spectra they get, and they are measuring how these clouds move in the atmosphere, how there are the processes of energy and composition and movement throughout it. So it's really detailed, high-resolution infrared information. That, if you compare with the HST, we're not going to do a lot of HST comparisons because I thought it's not about comparison, but I thought it was really good to illustrate, at least here, how complementary Webb and Hubble are. So there is a lot of Webb is, the successor or coming to substitute Hubble, and the answer is, well, no, because Hubble does a very different thing. It does visible, it does completely different wavelengths that is very complementary to Webb. And you can see it clearly illustrated here. With Webb, we can see these color clouds, thermal emission. You can see all the rings because they are composed by dust and ices, and that glows in the infrared. Whereas in the visible, you see a very similar view, but at different temperature, at different location in the stratus of the atmosphere, and you don't see the rings. So again, I always think of astronomical objects like, onions, because they have layers, and the layers have different temperatures and composition. And to really get a broad picture of what an astronomical object is and to understand it, you do need to have what we call multi-wavelength. You need your infrared and your visible and your radio, and so you need all the information you can get to actually get the fullest picture that you can achieve. So moving on, what I think is one of the, favorite planets for many people, Saturn. Saturn is beautiful, as observed with Webb. We can clearly see the planet, obviously, all these rings, and we can see the separation perfectly, and you can actually measure, it looks like you can even touch it. And you see here to the left of the image, a few of the satellites. They are in external rings. So now we're going to see, it is an animation. So at the beginning it's an animation to illustrate, what Enceladus is. I put a little mark in there, but the end of it is going to be actual data. So this is Saturn, and you have like outer rings that are usually not seen in the traditional pictures. And this is Enceladus. And this is actual data from Webb. So this is a plume of water that is really coming out of this satellite. And this was known, but so this water is coming through. It has like, I think they call them like tiger claws. It's had like cracks on the surface. This is an icy satellite, and underneath there is like water, maybe an ocean of water. So that water is sort of coming through and adding water to that ring around which is moving. So this is something that Cassini already saw, but we have never seen it in this incredible detail. And certainly, I think it was a surprise to see water everywhere with that spectroscopic data from Webb. So it was really an excellent result. And there's more to come, because you really want to keep on measuring all the satellites and the information and really understanding what's underneath all these cracks and these water oceans. Okay. The DART impact. So Frank gave us a great introduction before, so no need to include that. Just to say that this is something that, from the Webb perspective, it was a challenging observation, because stepping back, just going back to steps, most of the astronomical objects, when Webb observes them, they're like a static on the sky. So you just point and the telescope stays there and gets great data. When you're talking about solar system objects, and you've seen them, you've seen satellites, you've seen shooting stars, you've seen the planets moving through the night. So they move relatively fast compared with a standard, let's say, a galaxy or a faraway star. And so Webb has to use what we call tracking. So it needs to adjust its movement to the speed of that object, and then the object will look like a single point or a single object on the detector. And that's what we did with here. But the thing is that this object was 3 times faster than what was planned for Webb. But with the great support of the engineering team and everybody working on it, it was very successful. And actually now we can track objects faster than we thought we would. And this is the moment of the impact as captured by Webb. Another fun fact, this was the first collaboration between Webb and Hubble. So this was the first time that they both looked at the same object at the same time. And it was, again, highlighting, they do different things. They're just complementary. Okay. So we talked about solar system. In the solar system, there has been a lot of science and activity. Everything has been observed, like every type of objects, planets, asteroids, darts, impacts, etc. So it's really a very rich field, and it was just going to keep on thriving. But if we look farther away, there are other exoplanets. There are many other planets in the galaxy. Many years ago, we didn't know about them. I want to say that, let's say in the 80s, 90s, probably, we just knew our solar system planets. But then many planets started to get discovered and measured. And as of today, we know of at least 5,000 of them. So it's really a thriving field. And another interesting fact is that Webb was not designed or conceived to actually be a workhorse for exoplanets, but it is so well designed, and it works so well that you can actually use it very nicely for it, which is something that, again, pre-launch, there were these questions, so, okay, how well is it going to be able to do it? And the answer is, well, very well. You already saw this image before. These are 4 direct images of exoplanets. And I didn't mention it, but in the 4 little boxes at the bottom, the drawing with a star, that is where the actual star is. But with this technique we were talking about before, coronagraphy, you actually remove the star And we draw that in there just for reference, so you know that, yeah, there's an actual star, but this technique removes it so you can see what's underneath. And that's a planet in this case. That is for imaging. There is another very useful technique that we call transiting. And this is, again, another illustration video to show that. So this is a star, and you see 3 planets orbiting around. And to your left, you have the light curve. So you measure the light of the star, and when the first planet crosses in front of the star, the light drops. Then the second planet will cross, and the light will drop again. And the third, and so on. So the great thing about this is that, first of all, you measure the drop in the light, but you also measure the light as it filters through the atmosphere of the planet. That means that on that filtering process, you're going to be able to compare the light without filtering, the light without the planet in front, with the light, the filtered light through the planet atmosphere, and that will really tell you what is the composition of that atmosphere, what are the chemical elements, the chemical richness of the planet, and essentially give you ideas of how planets form and evolve and all the families that are there. So in astronomy, there's a lot of classification. So you really want to do families of objects, types of objects. So in the case of exoplanets, we generally talk about giant gaseous exoplanets like, Jupiter-like, and rocky exoplanets, more like Earth-like. And this is a very broad division, because then within them you also have different types. So there have been many discoveries and many first discoveries with Webb in this year. So this is, first of all, the first spectra we got with Webb. This was really quick, not a lot of time dedicated, but you see all these bumps. They are molecules and they are elements, and they are really telling us a lot about the richness. So the big things about exoplanets have been detecting water, carbon dioxide, carbon monoxide, sulfur, like a lot of this chemical richness, and also detecting chemical components that are evidence of that they have been generated by the influence of the stellar light in that atmosphere. So there is a lot going on, and there is a lot of comparison, and it's a field that is really thriving. So in the case of rocky exoplanets, and one of the things that many researchers are looking for is an exoplanet that has an atmosphere. And so far, we have looked at the TRAPPIST system, among many others. So TRAPPIST is very famous because there are many rocky exoplanets within, like 6 to 7, within, if you imagine our solar system, within the orbit of Mercury, there are many planets orbiting there, and they're all rocky. The thing is that the closest one to the stars, they are so hot that, the atmosphere just evaporated, and so far we don't have actual evidence of any of them. But this is one of the cases where there will be more data, there is more analysis going on, and there will be a lot of, I would say, interpretation, modeling, and data to come through. And, that's probably for next year and the years later. So in this plot, you can see Earth, and the temperature of Earth is slightly shy of 300 K. And you see the measured temperature for these TRAPPIST planets, which is, again, the first time we have measured. It's 400 some Fahrenheit, some 450 about the Fahrenheit degrees. And it is very hot, but actually in reality, it's the first time we have measured with this accuracy such a cold planet. It's not, it's not that cold compared with Earth, but it's really cold compared with many others we have measured before. So again, another first measured temperatures of some of these rocky exoplanets. Planets orbit around the stars. And stars have life cycles. Well, everything in the universe has a life cycle, but stars in particular have this, I would say, very beautiful life cycles, because from their birth to their death, they actually give us some of the most beautiful and informative data we can have. Stars are responsible for creating chemical elements, including everything we are made of, everything the Earth is made of. Stars are responsible for creating dust, and dust is a really important component of the universe because it gets recycled. So with dust from the stars that explode as supernovae, we're going to see some of that later, you can create a new generation of stars. You can enrich the universe with new elements. Even some very, very heavy stars can create gold inside, which is the same gold that coats the Webb mirror. So I think there is a lot of, there is beauty on the life cycle of stars, and there is a lot of information in it. So anyway, this example, this image here, it is an image of a protostellar disk. So if you notice at the center of this hourglass, there is like a dark horizontal bar. That is where a protostar it is forming. We don't see it because it has like a dusty disk around. What we see is the infrared emission illuminating all the dust and material around. It's like a double-sided jet. So at the top of the image, you see a more orangey glow because it is more dusty. And the bottom of the image that is like less orangey and more towards the blue. So generally speaking, in science, like blue colors is opposite as art. So in art, we say the reds are warm and the blues are cold. In science, it's usually it's the other way around. So the reds are colder, the blues are hotter. So in this case, the top part would be like color emission, the bottom one that is blue. So this is going back to the first anniversary image. This is Rho Ophiuchi, a very beautiful star-forming region, the closest one to Earth. And it's really, for a star-forming region, it is quiet. It only has like about 50 stars, about 1 solar mass, not very big, not very intense, although you wouldn't say that with this amazing activity that we're seeing here. And this is a case where the colors you can see are really important. So at the bottom part where you see, I see a flower, many people see different things, but that yellow part, it's really dust and organic components that are being the aftermath of the process of forming a star. And you can see at the center, there is a star, which is the most massive star of this group of 50, about 50 stars in formation. All the red sort of jets and activity going around, these are hydrogen jets that are coming from the protostars, similar to what we saw in the previous image. So there are protostars, stars forming disks. The disk, they start accreting. In that accretion process, the star starts to form, and at some point it ignites the hydrogen and it starts, it is a very energetic process that illuminates all the surroundings. So in this case, we can see a lot of, I hope you can see it, but right on the top part where the red arm is, right to the left of it, there is like an hourglass, similar to what we saw before. So that hourglass is again a disk in the center illuminating with a jet the material around. So there are many of these, and in many cases we will have disks around a star or a protostar, and some of these disks will start forming planets. And this is what we're going to see in the next image. So here to the left, you have the pre-JWST view of a very well-known debris disk called Fomalhaut. And you see like the star at the center, and there is this very nice ring of material around. To your right is what we see with Webb. Not only, well, you don't see the stars because it has been removed with this coronagraphy technique. But so if you remove the star, you can see the disk we knew was there from before, but you will also see an inner disk that is actually not flat. I mean, if you can see, if you notice, it has some inclination and even some like slightly rubbed, bended structure. So this is a disk where, potentially you could have planets in formation, and it certainly illustrates the importance of studying these objects and understanding them, because it provides the link between, how planets are formed and then the planets we see in the aftermath. Be our solar system or some exoplanets. So the study of protoplanetary disk is really important, and with Webb, we can see details, as you can see on this image illustrating here, that we have never seen before, literally. So it's really an exciting time to be part of this science, I think. Another very famous star-forming region. The difference between this one, this is the Pillars of Creation, and Rho Ophiuchi is that in Rho Ophiuchi we have about 50, and it's really close, and it's really astonishing in the details. This one, it's also beautiful and astonishing, but it has thousands of stars. And really, again, you see how not only you can see through the dust, like a lot of these stars information, but you actually see the dust glowing, and the things that many of these stars, they are almost about to sort of remove their cloaks of dust and shine like stars, but they still have these cloaks of dust. And that's why you see all these red parts and these sort of, that they look like activity. These are stars information. And all the dust that we see here is not only about the stars, you can also study the dust and the dust composition. And that's a really important piece of information, if you will, to understand not only the stellar cycle, but also how that dust fits into the galaxy evolution and into of course, the general star formation theory and evolution. So we talked about how stars are born. This is how a star like our sun, about 1 solar mass, would die. And it will not go out like a bright, shiny supernova. It would actually, this is what we call a planetary nebula. It is a misname for historical reasons, but the point is that at some point the central star, it will start expanding and will be like a red giant, and then at some point it will start shedding the outer shells as a way to control its own pressure and its own mechanisms. And this is what you see here. So you see, these are two different images because Webb, it's infrared, but it has, to your left, near infrared, so cold, but not as cold as the one to the right, mid-infrared. And the interesting thing is that you see here that in the mid-infrared, the one to the right, you see that actually this system has 2 stars, and the red one is the one that is shedding all these materials and shedding all these ejecting, essentially, and it's the one that is on this late phases of life. The future of a star that undergoes such a phase of planetary nebula is to essentially at some point shut down. It will start releasing more and more energy, and at some point it will run out of it and will just literally switch off and, I guess, drift into the universe. And this is the other extreme, because stars, the life of a star and the way a star, how long they live and how they die, it is actually determined by their mass. So the more massive, like this one, this is about a 30 times star, tens of times more massive than our sun, it really will go out as a supernova. But this is not quite yet a supernova. This is the Wolf-Rayet phase, which essentially means that the star, it is shedding enormous amounts of material into the universe, which is exactly what you see illustrated here. And these materials, as the star ejects the gas and the gas moves away from the star, it becomes dust and enriches the universe, and it may be the fuel for the next generation of stars. So this is a single Wolf-Rayet star, so very massive, will go out as supernova. What happens when we have this star orbiting around, actually the other way, another star orbiting around one of these? So this is what we're going to see in the next illustration. So you have the star approaches the Wolf-Rayet, and then when it approaches it, because of the gravitational pull of that interaction, the Wolf-Rayet sheds incredible amounts of dust and material. So how does Webb see this? This is how it does it. It is one of the most astonishing examples of a Wolf-Rayet with a companion. What you can see here are 17 rings. Each of these rings is ejected, if you want, every 8 years, because that is the period of the star that is orbiting around. That's when they get closer and then the material gets pulled. So this is the dust history of these stars, of this star for many, many years, captured in rings around the star. And Webb can see it, and I hope you can see the top right edge of it, because it's really astonishing, the amount of detail and information. And so this is like a fun archaeological project, if you will, to do on the dust composition of this star throughout more than 100 years. And it's only because it has a companion, and so it has this sort of gravitational pull. And again, when it comes to dust, there is some dust deficit in the universe, and Wolf-Rayets are one of those stars that stellar types that are actually responsible of enriching the universe with dust. So they are really interesting and very well studied. And this is how Webb looks at them. And finally, these last two stars will go off as supernovae. This is Cassiopeia A, a very famous supernova remnant. And so the star is gone. You see lots of material. So what are we looking at here? So we're looking at mainly three different things. So the first of all, you see like this arch of orange material on top and to the left. So that is not coming from the star. That is actually the interstellar medium and material that is just sitting there that got compressed with the blast, if you want, of the supernova. So in that compression, it is actually looks as if it was igniting, essentially. So you can see it glow, and you can see it how it's kind of activated by that, by the impact of the supernova explosion. The white material, it is coming from the star. It's like the remnant of the supernova, and then the green material inside, it's also coming from the supernova. But last time I checked, it was not really clear what it was, because the first year of Webb Science has given a lot of answers to scientists, but it has also given a lot of questions, which is exactly why we send these sophisticated telescopes to the universe, because we do want to keep on investigating and having more questions and having more answers and really get deep into the details. So this is the destiny of stars that are really very massive and tens of times more massive than the sun. Is just go out as a supernova. Okay, so stars live in galaxies. I like to think of galaxies as somehow the building blocks of our universe. And the stars, they live in these little neighborhoods that we call galaxies. So with Webb, there is a lot of extragalactic studies. We're going to talk now a little bit about nearby galaxies, and then we're going to move into like farther away galaxies and how they, how we're seeing them and what are the key findings, if you will, that we're seeing on that field. But I really wanted to make sure to show this image of a galaxy, because it's really illustrative and astonishing, and it really shows the power of Webb to study nearby objects. So you see all these bubbles that you see around. It looks like a lace, essentially. So all these bubbles are the after effect of star formation sort of blowing away materials and compressing it around it, and also supernova sort of blowing away material and sort of cleaning it. So this is a really key phase on, again, the cycle of star formation and dust, and it also helps understanding, because all the little red dots you see, they are stars being formed, and the bluer ones are older ones. And then at the center of this galaxy, you see a stellar cluster in blue, really beautiful and really in detail. So the advantage of studying nearby galaxies with Webb or with any other telescope, and to get a full picture of what they look like, how is their black hole at the center, how do they interact and evolve. So the advantage of that is that you can then, as a first guess, you can take what you learn in the nearby universe and compare it with what you're seeing in the faraway universe. And so you can say, okay, is this consistent? Does it make sense? Are we seeing the same, or was the universe slightly different when it was older? So these are all the kind of big questions, and why there's so much interest in studying galaxies and understanding how these the process of dust and formation and how stellar formation impacts it, and of course the black holes in the center, which Webb is seeing a lot of black holes. Okay, galaxy evolution. There is a phase. This is Stefan's Quintet, one of the most, to me, beautiful images we're taking, and this is really an illustration of a phase that we think every galaxy goes through, and that is called merging. So merging happens when two galaxies, or in this case, a few of them, 3, 4, they get gravitational, they get close, and so they start to gravitationally affect each other. And that means that they will get distorted. This is a perfect example. They will get misshaped. Oftentimes they will, as you can see in the middle of this image, they will compress the gas and material in between them, and in that compression they will create new stars and new materials in there. And the future of these galaxies in particular, we don't know. I mean, oftentimes, like interacting galaxies, they will become elliptical galaxies, like, bigger and, I don't want to say boring, but, kind of more quiet, not as this. In other cases, they will have like a few million years of interactions and this sort of cosmic dance, and then they will just separate because they were not close enough. So it really depends on how many galaxies, how close they get, and the initial angle and configuration with which they started interacting. This is an interesting one, and it illustrates well, I think, something we're going to talk about later, and that is that in astronomy we see everything in projection. So here we see this as a flat image, but you could think that, okay, all these, let's say 4 galaxies here, there's a 5th one, but we don't see it clearly here. They are together. They look as if they are together, and they look as if the one to the left, this sort of blue misshaped one, is also part of this group that is interacting, but in reality it is not. It is just a projection effect. The galaxy that is blue here is actually much closer than the other one. So it is a fun way of seeing, like, first thing, like, it's really, projection is important, and that's why often you need to, many times you can use images to figure out if things are close or not, but in many, many cases, especially when you are talking about really far away galaxies, you do need spectroscopy to confirm those distances and to make sure where the objects are with respect to each other. And again, at the top of this image, the galaxy in the center, you really see this shiny AGN. This is an active galactic nucleus. Nucleus that is very energetic, and the energy is fueled by the black hole at the center. Okay. So we're going to start looking back in time. And we're going to start, because the very original motivation to build and launch Webb was to detect and observe the very first galaxies. Of course, it's used obviously to do many, many other things. It's an observatory, which means that it's incredibly flexible, and if you can dream it in the infrared, you can actually do it with Webb. So it is, it has a lot of science potential, but this is kind of one of the original reasons why it was built. And I wanted to first start with the concept of, so we look back in time, but again, we use a trick to characterize a lot of the galaxies, and that trick is called gravitational lensing. So this is a galaxy cluster. There are many galaxies here that are together, and it is about half the age of the universe, about 6.2 billion years after the Big Bang. So this was, many, many galaxies, hundreds of them put together and interacting gravitationally. And what happens in this case is this is the most massive galaxy cluster at that time. So when the universe was half its age. And what happens in this case is that there is so much mass, there's really so much mass that the light from the objects coming from behind, it really gets distorted and amplified. And in that distortion and amplification, it is like having a natural telescope. So the galaxy cluster is acting like a natural telescope that allows us to see what is behind, magnified and with a lot of detail. And these are two beautiful examples for that. So you have this very thin, distorted galaxy in here. And often you will see that these lenses, they repeat. They have like repeated images. And again, there are techniques to understand if the repeated images are from the same galaxy or from another galaxy. And that's a spectroscopy. And this one down here, it's very well known too. This is called the hook for obvious reasons. And again, it's a galaxy billions of years older than the ones in the cluster. So again, we have like this natural telescope that is magnifying what is behind and allowing us to study in incredible detail all those objects behind. And this is, if you've heard about these very old stars that have been detected in galaxies, they live in this sort of galaxies that are distorted by a cluster, and then we can see them magnified and amplified, and we can measure them. So this is when the universe was about half its age. About 813 million years after the Big Bang, so very young universe, we have this first evidence of cosmic filaments. So for those of you who have seen like the cosmic Webb simulations, you remember there are like these little dots, bright dots. Those are all like future galaxies, and then connecting those dots, there are like these little threads, and these are like bridges of that dark matter that are in there. So this is all these little circles you see here. They are a group of galaxies that are sort of connected by a 3 million light year long filament. They are connected, well, they were connected, and the future for this group of galaxies connected by a filament will be to become a cluster itself. And this is providing the link between the very first galaxy seeds and the galaxies we see today. And it's all about having those links and filling in those gaps and try to understand better what we're actually seeing and how galaxies came to be, essentially to be what they are right now. If we go back further in time, we have this beautiful example of the 7 red galaxies on top. They are magnified because it's really hard to see them on the original image. But they are there, they are real, very precise measurements with first imaging, as you see here, then spectroscopy. So these are 7 red galaxies 650 million years after the Big Bang. So it's really, it's an impressively old collection of galaxies, and they are, again, of the same age. So they are like a protocluster of galaxies that are living together, or were living together, that would evolve into a cluster as the ones we see today. So again, it's all in these details and connections depending on different times of the universe we are exploring. If we go even further back in time, now we are going into these are some of the oldest galaxies Webb has seen. So the oldest one about 320 million years after the Big Bang. You can see it there. And this is, I love this plot to the right, because this is how we make sure that they are of that age. And essentially, you see this is a spectra. And of course, you don't have like very bright or incredibly booming lines because it's very faint and far away. But you always find, you search for this Lyman break characteristic. It's like a step on the spectrum. And then once you find that, galaxies have it because of the stars they have. So once you find that, you can make sure that what is the distance at which your galaxy is, or the age that it has. This is one of the oldest we have had. So we have measured so far. So when it comes to the old, the old universe, if you want, or the very distant universe, what Webb is measuring is a lot of galaxies. Galaxies did form as early as about 320 million years after the Big Bang, which is something we didn't know. Now we know it because we measure it. Many of these galaxies are, they are not very distorted. They are quite well organized, and they have their, they have bars and they have their arms, and they don't look like in this array, which, somehow surprising. And then there is a lot of activity on studying black holes, not only at very high redshift, but throughout the redshift universe. And in general, there are a lot of black holes, maybe more than were expected, and they are very, very massive, many of them. So this is just to say that before Webb, there were, this is something that usually people would say, or I've seen in the press a lot, like, Webb is breaking cosmology and all these sort of headlines. And in reality, it hasn't really broken up cosmology. It's just showing new data that we have never measured before. So this is a great new contribution. And now we need to adjust some of the models and some of the perhaps preconceptions we had to make sure that the data we have that is solid and that is actually real can fit those models. It's not that, and that's part of the scientific process and the discovery process. So you have a theory, and then you have to adjust it when you get data to actually verify it. This is one of my last slides, and it's just a video where we're going to go through, this is from the SEARS project, we're going to see it now, and it's an animation that really beautifully illustrates what we were talking about before, about the two-dimensionality of the images and the fact that everything is in projection. So we're going to have a fly-through, and this is based on real data. This is not a simulation. And as we move into the image and center on one galaxy that is really far away, all the galaxies that are getting behind us are the closest ones. And then you go deeper and deeper and deeper. And this is what the reality is in projection, but actually it's a three-dimensional information. I mean, you can see many of the nuclei details and arms and structures in here. And the galaxy we're going to end up focusing on, this is called the Macy galaxy. It's about, I think, 340 million years after the Big Bang. So again, very, very old. Not the oldest, but very, very old. And very interesting. And, okay. And I thought that I could close with this beautiful first anniversary image. I almost find it daunting in its beauty. It's really airy and inspirational, and I hope it inspires you as well. So that was my last slide. I think I'm going to stop sharing, and Frank now will.
That's right. I will come join you.
There you go.
Thank you,
Okay.
Monica.
Of course.
That was wonderful. Okay. What I liked best about it was that, as you said, we have these marquee science programs, the most distant galaxies in the universe, exoplanets, and that's sort of how you advertise Webb as is going to do amazing things on that. But what you've done with your talk here is you've shown how it studies planets, it studies stars and nebulae, it studies galaxies, it studies cosmology and gravitational lensing. So I think this is a great summary to show people that it's not a special purpose observatory, it's yet another general purpose observatory.
Absolutely, yeah.
So one of the things I wanted to ask you to clarify a little bit about is that a lot of our viewers were raised on Hubble images, okay? And when they see a nebula, right, they're used to talking about gas, the H2 regions, the hydrogen gas that's there. And yet you didn't say gas very much at all, this because you're in infrared and you're seeing dust. So can you comment on trying to help them understand how to go from used to thinking about gas and now thinking about dust when you're seeing in the infrared?
Yes. So I think a nice way of going around this is if you think of the pillars of creation image, the one that are like three big fingers, in the Hubble images, they were essentially dark pillars with a lot of emission around and with the stars around, but you could see that they were really, really dark because the dust is blocking the emission of the stars behind. So so in that case, you're not seeing the emission of the dust because it's just not, I mean, in the visible you won't see it, it just blocks everything. But then when you move to the infrared, you can really see colder objects. So you can see the dust grains because they have the right size and the right temperature to actually see them. And you can actually, there is a very interesting effect. It just happens that many of those stars, they actually glow. The dust serves as a screen, if you will, where it heats up and it re-emits the temperature of the objects behind. So you see both things. You see the stars, you see gas as well. You're right that I talked a lot about dust because, it's infrared and we are kind of obsessed with dust. But you see, it's not that you don't see the gas, you see everything. It's just that you see different temperatures, different compositions, and also different layers, because all of this is about layers, and what is maybe outside is hotter or blocked by the dust. But then as you go deeper with the infrared, you can see what's inside and what is colder, essentially.
Right. Yeah, and that's absolutely perfect because understanding that the infrared is seeing cooler temperatures. So in a nebula, the hotter temperatures are generally on the outside, and the cooler temperatures are inside. So you're seeing deeper down inside it. And I just always love the galaxy images where it's like you're seeing that dust, the spine of the galaxy that's composed.
Oh
of
my
dust.
God, that image!
Isn't that great? Yeah.
It's amazing. I love that one.
And it's opaque, invisible light. And now we get to really see it and study it, which is great.
Exactly.
All right. So we've had a good discussion going on in the chat on YouTube. Grant, would you turn on your camera and join us? Grant has been following the chat on YouTube. Do you have some good questions for us tonight, Grant?
Absolutely, I do. The chat has been great, and they've also been answering some of their own questions. The dust discussion would make you very happy.
I love that.
All right, so I'm going to get us started with our first one. Are the spectrum colors selected by different optimized gratings in JWST?
That is correct. So so we have, you select with gratings and then you disperse them. So there is, depending on the instrument, a combination of different gratings and dichroics. So in the combination of the dichroic and the grating, you select the spectral band if you want, and then disperse it.
And when you talked about the MIRI instrument, you talked about all the different bounces it had to make. I mean, if we had a telescope that was really, really long that you could actually that you had lots of space, you could actually do that all in a much more direct pathway. But it's because you only have a certain meter size, something to work with, that you have to bounce it all around before you can bring it to the focus properly.
Correct. And actually, that is. From an engineering perspective, that design you saw, it's really, I just love it. It's very compact and optimized. And yes, like I knew the number of bounces in the past. I don't remember it now, but you saw it. It's just a lot of them. And it works really well, but you're absolutely right. If this was if you had a bigger space, then you could optimize your design differently.
And it always surprises me that you have so many bounces, because at each bounce you sort of lose a little bit of your light, and yet JWST's efficiency is so great. I mean, yeah.
Yeah, so. I mean, there is a lot to say about how well the surfaces are polished and how clean they are. So contamination control was a big part of the whole, testing and building and design. But yeah, you're absolutely right. If we wouldn't have all those bounces, you'll get a little bit better because you're not losing anything.
But it's still doing amazing things, even with
exactly.
that slight, tiny little handicap. All right, Grant, what else we got?
Sure. Yeah, the efficiency is incredible. In what part of the focal plane is the coronagraph placed?
The coronagraph is we have the imager focal plane and the detector, and there is a plate. It's like a literal plate where you have I'm talking about MIRI right now, but you have the Leo mask and the other coronagraph that use a different technique. So it is kind of attached to that focal plane.
Okay.
And we have coronagraphs both for NIRCam and for MIRI, correct?
Yes. So for NIRCam is a slightly different technique. So with NIRCam, you sort of have to move them in the field. and they use bars mostly, but it's a similar concept. It's just again design choices because of the different needs of the instruments.
So when you showed the observation that used both NIRCam and MIRI, of course, those had to be separate observations, and the telescope probably had to be slewed in between those to do it.
Correct.
Okay.
So yes, you can. So if you think of the focal plane of where like the telescope looks at the sky, each instrument has like a space in the focal plane, and you can use two at the same time, but they look at different things. So yeah, if you wanted to do the same thing with two instruments, you have to move the telescope.
Great.
Gotcha. Makes sense. Okay, so let's see here. Has JWST, if you were allowed to talk about it, has JWST done any observations of black holes that you are aware of, and can you speak on any of it?
There have been. So black holes are a big thing for astronomy in general, and yeah, Webb has observed. Observed. I would like to rephrase that as indirect evidence and measurements, because black holes, like, we don't really observe them directly with Webb. You see like their sphere of influence and the surroundings and what happens around them. But yes, many black holes, many of them, kind of a lot of them at many different times of the universe. And we're talking about black holes of literally millions and billions of solar masses in the galaxy. So there is a lot of ongoing effort on understanding, first of all, how they came to be originally, like where are they coming from, how were they created, and then how have they evolved to present days black holes. So yes, there is a lot of black hole activity, if you want, with the Webb.
But not necessarily a direct observation. It's been tangentially related to other observations. Okay.
Right.
So the real answer is not yet.
Well, it's like if you drop a pen, it will fall because of gravity, and that's evidence of gravity. It's a similar thing. So evidence of black holes are, for instance, like in our own galaxy. Like if you look in the infrared, you would see like stars orbiting around, and you would see like when the black hole emits energies, every now and then you see like around it the material glowing. So you see all these secondary, if you will, effects.
And even the images of black holes that have come from the telescopes are actually images of the material around the black hole. These are the accretion disk around the black hole, the M87 and the Milky Way one. They are not actually seeing the black hole because it's black and it's not going to be seen no matter what you do.
Right. It's like at a different level, it's like we don't see the Big Bang, right? Yeah. We know it's real and we know it existed because we measure the expansion of the universe, and there are many evidence that are solid and that are consistent with that, but it's not that we're not going to see it with Webb, essentially. Or anything.
All right, so I'm going to jump in with a question because I know that our audience members are thinking this because somebody always asks this. Looking back at the first year, there have been a number of surprises, at least for me, in going through the press releases as we present them. What to you was the most surprising of the Webb discoveries?
I mean, for me, at a very personal level, it was even before we started to do science, when we were doing like the half a year after launch commissioning, that is, getting everything ready to do science. For me, like the very first images that we took with enough quality, that was a public image, actually. Remember the image where there was a star, very bright star in the center? It was like, okay, the mirrors are perfectly well aligned and this is fantastic. But if you look at the background, oh my God, the sheer number of galaxies in there, that really blew me away. And that's where I think we all knew this was going to be incredible, because that was the first, all these galaxies. I mean, I always say that, for this period, we had like all these programs where you say, I'm going to observe this isolated object and characterize all these things based on that single isolated star. And of course, there was no isolated star ever. You always had a galaxy here and this thing there and a cloud of dust. So it was, yeah, that was a very surprise to me, like how well it's working and the potential of discovery. And then for the science observations, for me, all the discoveries of the high redshift universe, like all these filaments and really far away galaxies, it just really blows my mind, really.
I have to agree with you that the number of background galaxies is just stunning, because we did a visualization of Stephan's quintet where we were comparing the Hubble and the Webb images. And just the way that the distant galaxies were so well observed in infrared, that you're getting to the low mass stars, that you're getting to the redshifted light that Hubble doesn't see, and you're really getting those background galaxies just pop so much more than we see with Hubble, even and in less time, because Webb is doing it in a shorter exposure than Hubble had to do theirs.
Oh, yeah.
And that's just this discovery potential for the distant universe is just off the charts here. I have to agree on that.
I've got 3. If we can run them quick, is that okay?
Okay. All right.
That's okay with me.
All right.
Yeah.
First one we got to get out of the way, because every time we talk about JWST, someone asks some variation of this question. Why won't JWST look at insert solar planet here, like Pluto, Jupiter, whatever? Somebody always asks.
We have looked at Jupiter.
Yes.
Yes, but general point, like why is JWST not observing things that are closer versus than farther away? It's a general question we get about every time.
Okay, so I think maybe there is a misconception here. So we are looking, the solar system is being explored, I don't want to say intensively, but there are a lot of programs for the solar system, like all the planets that can be observed with Webb where it is, right? They are being observed, and not only planets, but asteroids and serendipitous discoveries of objects moving in your field, etc. So there is a lot of that going on. I think there are certain biases on the press, and certainly things like galaxies, they get a lot, in my opinion, they get very highlighted, and we are always chasing for the farthest away and the faintest and all this, but that doesn't mean we don't do all the rest. Actually, I think for a year there is a good balance in the science of all the programs. And yes, galaxies, they get a huge portion of the time, but for instance, exoplanets, they get a significant portion, and I would say maybe not as much, but comparable. So it's also a matter of, to observe these distant objects, you need more time. So with the solar system, like with a planet, it's so bright. You can do it like that. Move the telescope a bit and you take data. For other things, you maybe need to dedicate tens of hours. For an exoplanet, you certainly need to dedicate tens of hours. So I think there is also that, like how long do you need of telescope time? But I think it's a well-balanced portfolio. I think the solar system, I don't feel they are not being taken care of, if you will. And if you look at the webtelescope.org, well, not you, but whoever in the public, there are a lot of press releases and information there. And also the science portfolio for Cycle 2 is public information. So whoever is curious, they can go there and actually check it out.
That was going to be my follow-up, is where can they go to see the things that may not be popping up in the news as much? So webtelescope.org for sure.
Or also in the JWST Observer.
Mm-hmm.
All the programs are there, and whoever is really interested on this sort of more observer questions like programs and all that, they can subscribe to the JWST Observer News, and they will get all the, like the Cycle 2 has been announced, and these are the programs and all that. It is there and it is public.
Right, and that's important, because sometimes the people don't think that that type of information is public. that
Yes.
the programs that are selected for Hubble and for Webb time are announced, and they are out there, and people know what the telescope is looking at. So other observers know it as well. All right.
And actually, even, oh, I'm sorry.
Go ahead.
Can I add
No, go ahead.
super quick? Even the information of what is the telescope going to do next week, that is public. People can actually go and look for that.
All right, Grant, last question.
Absolutely. Will Webb serve to identify things such as brown dwarfs and rogue planets?
Brown dwarfs, they have been observed, and there are many studies about brown dwarfs. I am not personally aware of rogue planets, but if you can find it, you could observe it. That would be my take.
I always think
That's
of
really the biggest takeaway. Yeah.
I really think of rogue planet discoveries as somewhat serendipitous, right? Because if it's a rogue planet, it's not where it's supposed to be. So, I mean, how do you point towards it?
Exactly.
It's the kind of thing that maybe Keck will uncover it, and JWST will do follow up to get the fine detail about it.
Exactly.
All right, is that all we've got, Grant? It's about time.
Do you want to sneak one in, or we want to call it?
If you got one more, I'll let you sneak one more in. Okay.
All right. Will JWST be able to take ultra deep field surveys looking in directions that we haven't already seen, or is it already doing so?
So the thing with the answer is yes, you could. I mean, you could point anywhere and integrate to your hard content. The thing is that you usually want to make use of this multi-wavelength approach we said before. So it is very common to go to well-known and well-studied fields because there is already built-in knowledge, and then you're going to go and you want to go there and add up to it. You want to see, let's take the Hubble Deep Field, for instance. So yes, that was like a no-brainer for Webb to go and observe. So yes, an observer could apply for that, and it could be certainly it is a possibility, but it's always I think you always want to build up on, let's say, the shoulders of all the previous missions and really contribute to all that knowledge.
Right.
That's a big difference in the telescopes that I don't think a lot of the public is necessarily aware of. Is it's not just like an observation. It's series of observations. It's lots of data. It's building models. It's updating the information we already have with where it is now that we've observed again and building it out as a whole unit. It's not just like, here's a picture. It's here's this, and we're using it to recreate what's there so we can find out more about it. And each time we reobserve it, you add data, which gives you a better idea of where it was and where it's going.
Exactly.
Yeah. Frank,
yeah,
go ahead. Sorry.
And that's always been our message, is that Hubble and Webb work together to give us more information about the universe. And especially when it comes to these deep field surveys, Webb is just really pushing things in a new direction, extending things well beyond what we were able to see before. All right. Well, thank you, Maka. That was a wonderful talk.
Thank you so much for having me.
Wonderful to have you here. To our audience, we will see you next month. Actually, I won't see you next month. I will be on vacation and out of the country, so you'll have a special guest host who I don't know who that is going to be yet, but I'll make sure I have one for you. September 5th. You want to understand the difference between gas and dust? Well, that's all about the interstellar medium, and that is what you'll hear about on September 5th. All right? Until then, thank you all for joining us, and have a great day.
All right, we're good.